One of the ultimate goals of astrophysics has always been to work out when the first stars formed in the universe. And we can actually do this because light takes time to travel to us because it travels at a set speed limit. So as we look back at more distant and more distant objects, we're seeing them as they were when the universe was much younger. So as we use telescopes, we're seeing back in time, which means it technically should be possible for us to observe the time in the universe when the first stars form, figure out when that actually happened and what those first stars were like. Now you might have heard people talk about how incredible the James Webb Space Telescope is and how we can see galaxies further back than ever before. And yeah, it was literally pitched as we will see the first galaxies in the universe that contain the first generation of stars. But that era of the first galaxies forming is a long time after the era of the first stars forming. And generosity can't see that far back. Objects get too faint and it's not got a chance in hell of resolving an individual star at that great of a distance. So instead, if we want to do this and we want to observe the era that the first stars actually formed in the universe, we have to get a little bit clever and we have to use radio astronomy to try and detect the impact that the first stars to ever form had on the hydrogen gas around them. To pinpoint, how old was the universe when the first stars formed and fill in that little missing piece of the puzzle in our best theory of how the universe evolved. Now, people have been trying to do this now for years with ever-growing radio telescopes. And there was even a tentative claim of a detection back in 2018 from Bowman and collaborators, which has been under a lot of scrutiny in the past few years, and now people don't believe that it was an actual detection that was made. Instead, everyone's hopes are resting on the Square Kilometre Array, the SKA radio telescope that's under construction right now in Australia and South Africa and should start operations around 2027. So in this video, let's dive into first, what are the first stars, known as population 3 stars, thought to be like? Second, what impact do they have on the universe and how we'll use that to pinpoint when they start forming? Third, what Bowman and collaborators in 2018 found with their tentative detection. And finally, how the SKA should be able to help with this. And if you want to know more about the SKA after watching this video, including opportunities to actually get involved with this massive project, check out the official SKA Observatory website. I'll link it down below. Now, websites like this are all written in HTML and JavaScript coding languages, which can look incredibly complex and, let's face it, overwhelming if you've never coded before. And that can be a really big barrier to creating a website. Maybe you need one for yourself to represent yourself professionally, or maybe you need one for your business. And that's where Squarespace comes in, the sponsor of this week's video. Squarespace makes creating a beautiful, professional looking website that helps you or your brand stand out online just so incredibly easy. Everything is just in one place and they've got templates if you're not so great at the artistic side of things like me. Plus everything's just simple drag and drop, so there's no coding skills required. They've developed design intelligence, combining 2 decades of industry-leading design expertise with cutting-edge AI technology to empower you, right, to create a bespoke digital identity online. And even though I know how to code, there are some bits of website design that I just have absolutely no clue on, like taking payment for products or scheduling content or membership areas. But Squarespace just makes all of those really difficult things so easy and streamlined, from scheduling meetings with clients to selling products to sending email newsletters. So what are you waiting for? Head to squarespace.com for a free trial, and then when you're ready to launch the website that you've created, head to squarespace.com/Dr. Becky, or you can scan the QR code and you'll get 10% off your first purchase of a website or a domain. So thanks again to Squarespace for sponsoring this video, and now let's dive in and chat about what are the first stars thought to be like. So when we look at stars like the sun and split their light into the rainbow of colours, we actually see that there are gaps in the rainbow. So there's missing colours of light where a certain element in the material that makes up the sun has absorbed that colour before the light is radiated out into space. So it could be sodium or helium or even something as heavy as iron. We call these missing gaps metal lines because for astronomers, anything heavier than helium is called a metal to us. But if we look at older stars in the Milky Way, we actually see that they're missing these metal lines and therefore they are metal poor. They have less of those heavier elements in their big atmospheres, in the star, and instead are made from a purer mix of just hydrogen and helium with a trace amount of metals. In fact, the purest star we've ever observed in the Milky Way is SMSS J1605-1443, which has less than a millionth of the iron content that the Sun has. And so you can split stars roughly into those two overarching types. So the younger, more metal-rich, what we call population 1 stars, and the older, metal-poor population 2 stars. And this dichotomy of split between sort of like the correlation between age and the amount of metals, the amount of heavy elements in stars, makes sense if we think about what the Big Bang Theory tells us. That in the early days of the universe just had some hydrogen, about 75% hydrogen with about 25% helium, and that was pretty much it. It's stars that make the heavier elements through nuclear fusion. That's how they power themselves and give off light and heat. So in the center, the core of the sun, it's fusing hydrogen into helium. And when it runs out of hydrogen to fuse into helium, it starts to fuse helium into the heavier elements. And then once stars die in a supernova or a nova, they disperse those heavier elements out through space. You can think of stars as like polluting that pristine hydrogen and helium gas of the early universe, so that as more and more new generations of stars form, they form from that more polluted gas and will contain more heavy elements, more metals. And that's why the sun, which formed 9 billion years into the universe's lifetime, is so metal rich. Which means if you think about it, the very first stars to have ever formed in the universe won't have just been metal poor, they would have been like metal free, forming from that pristine mix of hydrogen and helium gas in the early universe. And the fun thing is, they could form way more massive, so way heavier than the stars that we see today. And that's because heavier elements help to cool down hydrogen. You actually need cool hydrogen to form a star because otherwise the molecules have way too much energy and gravity can't clump it together to make it dense enough to form a star. So what happens is that a very light hydrogen atom comes in and hits into a much heavier metal atom, and the metal atom takes all of the energy from the hydrogen. That's barely affected, but the very light hydrogen is then like, oh, I've been stripped of energy, and it cools down. When the atoms are cooler, they clump together under gravity and collapse and form a star. But doing that quicker means you get smaller portions of these huge gas clouds that have cooled and can collapse and form lots of individual stars. Whereas if there's no metals, no heavier elements to cool that hydrogen gas quicker, you'll end up with a more sort of distributed cooling across the entire gas cloud as just hydrogen molecules bump into each other, which means you get the entire gas cloud collapsing down and forming a star. So that's why we think the very first stars to form will have been much bigger than what we see today. So the biggest stars that we see forming today are around about, say, 150 times heavier than the sun. Whereas we think the most massive population 3 stars that could have formed, these very early stars in the universe, are thought to form up to 1,000 to 10,000 times heavier than the sun. But with all of that extra material there, the crush of gravity is stronger, which means that they have to use up the fuel in the center of the core of that incredibly heavy star at a much faster rate to counteract that bigger crush of gravity, which means these very first stars in the universe that could get that massive won't have lived very long at all, only for a few tens of thousands of years or so. So they're not still around today, right? We've nothing like this in the Milky Way that's that massive. These kind of stars have already lived and died a long time ago, billions of years ago. So do we even have a hope of figuring out what these first stars were like? Well, that brings me to the second part of our story. What impact do they have on the universe, and how are we going to figure out when the first one formed? Well, because these first stars in the universe will have been able to form much heavier than the sun, they'll also be a lot hotter and a lot brighter as well. So for example, like a star that is 100 times heavier than the sun will shine with an energy of 1,000,000 suns. So things that are like 1,000 to 10,000 of times heavier than the sun will have been giving out so much high energy radiation. So not just light in visible wavelengths like we see with our eyes, but the majority of the light will actually have been in like ultraviolet light. And it's this ultraviolet light that's thought to have transformed the early universe entirely through a process known as reionization. So, a quick history of the universe according to the Big Bang Theory. Well, we all know how it goes, right? The whole universe was in a hot, dense place when expansion started 13.8 billion years ago, which meant that in the first few 100,000 years of the universe's lifetime, all you had was the basic building blocks of matter, protons, and electrons. And you just had these particles completely separate, whizzing around the universe and not bound together in atoms. We say that the universe at this point was ionized. Eventually though, the universe cooled enough thanks to the expansion, sort of spreading out the energy, which meant that these electrons and protons could be bound together in atoms for the first time. And that's how you ended up with like 75% hydrogen and about 25% helium, just a trace of slightly heavier things like lithium. But that also meant that you could have light traveling for the first time in the universe. Previously, light was just bouncing off all of these free floating particles, but now light could travel freely, and so this is when you get the first light in the universe, known as the cosmic microwave background, at this point that we call recombination of these particles into atoms. But after that light has escaped and dispersed, there's no other sources of light in the universe, and we enter what's known as the cosmic dark ages, where the universe was actually pretty opaque at this point. So if you've got neutral hydrogen gas, it's opaque to visible wavelengths of light like what we see with our eyes. And then eventually you'll have it cooling enough that you'll get the first stars to have formed, you'll get that light again in the universe, what we call the cosmic dawn, and all that extra ultraviolet radiation will impact with the neutral hydrogen around these newly formed stars, giving more energy to the electrons again, freeing them from being bound in atoms with those protons, and so the first stars start to reionize the universe in bubbles around them, making the universe transparent again, one star and one bubble at a time during a time period known as the epoch of reionization. Now, although we hope that with the James Webb Space Telescope, we can detect the light from some of the first generation of stars in galaxies, like close to the end of the epoch of reionization. Pinpointing exactly when the first stars formed and kicked off this process of reionization is when we have to start getting clever with radio astronomy. So neutral hydrogen does actually give out some light. So if you have the electrons bound in orbits around the protons, it can either be spinning up or spinning down, and it can spontaneously flip between the two. And in that process, it's a different energy amount that the electron has to be spin up or spin down, so it gives out that energy as light, and specifically as radio light with a wavelength of 21 centimeters. Now, it is incredibly rare that for any single atom that this flip will spontaneously occur. But if you have enough hydrogen there in a huge big cloud of gas, for example, like in the early universe, then you've got enough atoms there that there will be a signal of this 21 centimeter radio light from that hydrogen that's there. But as this reionization starts to occur, that signal of the 21 centimeter wavelength light should get weaker as more bubbles of this ionized hydrogen are formed by those first stars, which doesn't emit this 21 centimeter wavelength of light. So if we can track how much of this 21 centimeter wavelength of light we receive at different distances, so different points in the universe's history, then we can pinpoint when did reionization start, and therefore when did the first stars form, which we can do thanks to redshift. The universe is expanding, so light gets stretched to longer or redder wavelengths as it travels across expanding space from the early universe to the universe today where we detect it. So because light is stretched to longer wavelengths, which for visible light is redder colours, we say it has been red shifted. So 21 centimeter emission that's been given out by this hydrogen in the very early universe will have been more redshifted than 21 centimeter emission from, say, the end of the epoch of reionization, when the first stars have done all their job and all the bubbles have merged into one, where it will be less redshifted. So if we plot out the amount of light received in the wavelengths or frequencies where we'd expect this 21 centimeter emission to end up redshifted to from how long it's been traveling through the universe, and we compare that to the average background of how much 21 centimeter light we're getting from the whole sky, then we should see a dip with a shape that traces when reionization starts and ends. The problem is actually detecting that compared to the background of what's going on in the sky at these wavelengths or frequencies of radio light, because there's a lot of other things that give off radio wavelengths of light, not least of all the gas in our own galaxy. So this whole effort is complicated by what's known as foreground removal, basically modeling for the light that's being given out in the foreground, like in our own Milky Way galaxy, that's in the way of the signal you actually care about in the background. For example, we also have to do this when we observe the cosmic microwave background from the early universe as well. And people who work in this field really just end up like stuck in the weeds of like analyzing data from radio telescopes to work out like what's stuff in the foreground that we don't care about, and is there actually a signal in the background. Which brings me to part 3 of this video, what Bowman and collaborators claim to have found with their tentative detection of this in 2018, using something known as the Experiment to Detect the Global Epoch of Reionization Signature, or EDGES, a radio telescope located in a radio quiet zone at the Murchison Radio Astronomy Observatory in Western Australia, which was specifically designed to try and detect this drop compared to the background in the sort of redshifted 21 centimeter radio emission of light, hopefully coming from the epoch of reionization. And here's what their data looks like. So in panel A, this is what you first detect. It is completely dominated by gas in the Milky Way emitting light at these wavelengths in the foregrounds, which is obviously much, much brighter. So the first thing you have to do is model for what that emission should look like based on how much gas we know is there and how hot it is, and therefore what wavelengths of light it should be emitting, and then subtract that off from what you've observed. That's what's shown in panel B, right? You get what is left over when the foreground has been removed. And you can see there is a shape in the signal there that looks like a drop-off. Which, if you model that drop-off by what's shown in panel D, subtract it off what's shown in panel B, you get what's shown in panel C, what's known as the residuals, like what's left at the end, the noise in your data. So that looks like a pretty convincing detection of like a drop-off that's happening because of this epoch of reionization, except for a few problems. First of all, the frequency that it was detected at was in the middle around about 78 megahertz, which is a wavelength of about 3.8 meters, instead of the 68 megahertz it was expected to be at given our best model of the universe and the constraints we have from the James Webb Space Telescope of the most distant galaxies seen. Now you might think, okay, well then is this detection showing us that this like epoch of reionization and the moment at which the first stars formed happens later in the universe's lifetime than we thought it did, right? The numbers that we get here is that it starts, the first stars form at around about 180 million years into the universe's lifetime. It's a redshift factor of about 20. Except for the fact that this apparent detection was also twice as deep and much more flat-bottomed than it was predicted to be as well. Which started to raise some red flags for people. It meant that either there was something wrong with the instrument, with EDGES, or there was something wrong with how the analysis had been done, maybe like that subtraction of the foregrounds, or there was something wrong with our theories of how we think that stars form in the early universe, or maybe it was all 3 of those things. And people started thinking of ideas that, okay, well, what could explain it in terms of like the physics? You know, maybe the primordial hydrogen gas was cooler than expected, or maybe you could explain it if dark matter was different in the early universe. But before you go tweaking with all of those things and coming up with ever more outlandish ideas to try and explain this detection, you kind of have to confirm that there's nothing wrong with the instrument first, or our models for those pesky galactic foregrounds of radio emission that are in the way. And Bowman and collaborators were very careful to state all this, and they sort of doubted their own detection, to be honest. Really, the best way to try and confirm or deny this would be to try and make the detection again with another radio telescope to repeat your experiment. And thankfully, the shaped antenna measurement of the background radio spectrum, or the SARAS experiment, has done just that. And Singh and collaborators reported in 2022 that they didn't find the same signal as Bowman. Again, here panel A shows what they first detected that's very dominated by those Milky Way foregrounds, the gas in a Milky Way emitting the same radio frequencies. They modelled for that and then subtracted the foregrounds away, and after that, that's what you get in panel B, and there's no signal there that looks like what Bowman and collaborators found that's shown down there in panel F. So it seems like whatever it was that Bowman and collaborators found in their data, as Singh and collaborators put it, it wasn't astrophysical in origin. And to be honest, it's not actually that surprising given the fact that the current generation of radio telescopes that we have just aren't sensitive enough to detect the change in the amount of radio light received. We're still a few orders of magnitude above where we need to be. So finally, let's chat about how the Square Kilometre Array, the SKA, is going to help here. For radio telescopes, it's all about two things: the effective size and the number of antennae you have. So size is important because the bigger the telescope you have, the smaller the thing that you can make out on the sky. The more you can zoom in, essentially, and see finer details, whether that be smaller objects in our own Milky Way that are indeed actually smaller, or that are further away and only appear smaller because of their distance. The equation that you need to work this out is that the resolution, so the smallest thing that you can resolve, is proportional to the wavelength divided by the diameter of your telescope. So for shorter wavelengths of light, like visible light that we see with our eyes, you can get away with a smaller telescope, like the Hubble Space Telescope, for example. But if you want to get the same resolution with a radio telescope that's looking at the sky with much longer wavelengths of light, then you need to compensate for that by having a much bigger telescope, which is why you see these huge radio telescope dishes. But it's also why you see multiple antennas spread across an entire country or even an entire continent, right, that are combined to give you one effective telescope the size of the distance between the two most distant antennae, meaning you can resolve tiny detailed things on the sky even in radio wavelengths. But if you just have two antennae separated by a huge distance to give you like a radio telescope that is effectively that size, yes, you will see very small things on the sky, but you'll only see the brightest of things, right? Because you've only got two antennae collecting light, right? So you won't be sensitive to very faint things, like, for example, background signals from the epoch of reionization. So what you have to do is fill all that entire area with more antennae that can collect more light. Basically, with a radio telescope, the more antennae you have, the more sensitive to light you are. So current radio telescopes like LOFAR or the MWA have around a few thousand to tens of thousands of antennae to do this 21 centimeter detection. And as we saw, they're not reaching the required sensitivity to do this. You need more antenna, which is where the Square Kilometre Array, or SKA, comes into play. It's currently being built across two sites, one in South Africa to detect the higher radio frequencies and one in Western Australia to detect the lower radio frequencies. It's the lower frequencies that we care about for this 21 centimeter detection from the epoch of reionization, and the plan is to put 131,000 antennae, most of which will be clumped in a core that's about a kilometre across, with the rest spaced out over 75 kilometres. With that many antennae, we should be able to detect this. And with lessons learned from trying to do this with the likes of LOFAR and EDGES and SARAS, we have the data analysis pipelines ready to go, so that hopefully not long after the SKA starts operations in hopefully 2027, we will have another upper limit point to add to this diagram. And then slowly, as more data is taken, we'll bring that limit down and down. And hopefully finally agree on whether we've actually made a detection of this red-shifted 21 centimeter radio emission from the beginning of this epoch of reionization, and pinpoint exactly when in the universe's lifetime did the very first stars form. When that was. So difficult when like you're doing the science now, but the thing happened ages ago, so it was or it is, I don't know the tense. Oh, hair in my eye. Hair in my eye. Ah. What are the first stars thought to be like? That was stars and thought merged together in my head so that it became thought. It's not even a word. Burn. Not burn. Nuclear fusion isn't burning. I got 21 centimeters of light. I got 21 centimeters of light. I got 21 centimeters of light. Gotta go. No, I think we're good. I think we're good. I think we're good. Is that how that song goes? It's like 21 seconds to go, right? I got 21 seconds to go. I haven't thought of that song in so long. I think it must have been on like a now... the 37, I don't know what number of now.